So I think it's already time, so let's start. Hello, everyone. I welcome everybody at ninth lecture of our astrochemistry lecture course. This lecture will be given by Rob Garrod from University of Virginia, USA. Rob, please, the floor is yours.
All right, thanks very much, Sergey. Okay, so good morning, everyone. Okay, so yes, I'm going to be talking about chemical modeling, or astrochemical modeling is perhaps a better term. And I'll be saying something about reaction networks. I'm not going to get too much into which network is which and the histories of the networks and things like that. That information obviously exists, but what I want to do is give you all an idea of the kind of reactions that are important in sort of typical astrochemical simulations, and talk about some of the modeling methods. And one of the things I have in mind as I do this is that I hope you will try to do some astrochemical modeling yourselves. I'm sure some of you are interested in that. And I have a fairly simple astrochemical model available on my website. I'll give a link to that in a second. That you might find worthwhile to just try. And so I've got in mind that the information I'm going to tell you is going to be useful, especially if you are interested in running chemical models, either the sort of simple one I'm going to give you, or if ultimately you're interested in running models for sort of serious applications. So anyway, so my class is going to be split into two parts today. Let me just tell you what the main sort of themes are going to be then. So I will tell you some technical details about chemical models and about the chemical processes that take place in the interstellar medium. I'm assuming that you've already had some, quite a lot of very, well presented descriptions of the kinds of processes and the kinds of physics that are going on in the interstellar medium. I want to get into the sort of more technical details of the chemistry side of things. I also want to give you a bit of a feel for the quantities. It's not always, there are a lot of reactions and processes involved, but it's good to have a kind of a rough idea of the values of some of these quantities and so on. So hopefully that's something that you will get from this. As I said, there's a simple chemical model that is available to you or anyone else who wants to use it, and it's there on my website. There are also some instructions on how to practically run that model, and I don't want to get into that today. That's not really a good use of our time, but it's not tremendously hard to run. But it is a Fortran model, but that shouldn't stop anyone from using it. It's not hard to run or anything like that, and you don't need to know how Fortran works. But many of these actual models that we use are often written in some form of Fortran. But anyway, that's available online, and as I say, the information I give you today hopefully will make it a bit easier to understand what that model is doing, for one thing. But also, ultimately, I assume most of you have an interest in pursuing astrochemistry, either casually or fairly seriously. And you may be interested in running some astrochemical models yourselves. So hopefully this will give you enough information, at least to get started, and not to feel like it's too complicated of a subject to get into. So, all right, so overview then. So there's going to be two parts. So I'm going to concentrate on gas phase chemistry. As I say, that the model that I have available for you online is primarily a gas phase chemical model. So I'll say something about the models, about all the processes, to a certain extent where we get the rates from, and then I'll tie all that together and talk about some of the key reactions for certain key species. So obviously there's a lot of chemistry, there are a lot of species. I can't talk about everything, but I'm going to try and highlight some of the key processes for important molecules. I think what we'll do at that point is we'll take a few questions, and then we'll push on and then talk about grain surface chemistry, so chemistry taking place on interstellar dust grains, how we form ices, and then I assume you've heard something about ices in the interstellar medium already. I'll say something about the production of complex molecules. That's actually a somewhat of a controversial topic, depending on who you ask. People have slightly different ideas. I will give you at least the grain surface chemistry perspective. Then I will finish up just briefly mentioning, I think, some of the pitfalls and limitations of chemical models. I won't go over that in too much depth, but I'll point out the main ones. Okay, so let's get started. So I want to, I think it's useful to point out the differences between interstellar or protostellar chemistry and the kind of chemistry that we see in the lab on Earth. And maybe that's most useful, for those people either who are degree level chemists, or maybe you just remember doing high school chemistry or something like this. So a lot of the chemistry that takes place in the interstellar medium takes place in the gas phase. Obviously, it's not in solution, and so that is a difference from lab chemistry. In the lab, at least in a high school chemistry lab, pretty much everything is taking place in solution. That's not the case in the interstellar medium. It's all, all these processes we'll talk about over the next hour, I guess, take place in the gas, but it's still collisions that drive the chemistry. Okay, so we can still think of chemical rates as being driven by rates of collision, and so that's the starting point if we're taking a theoretical point of view of how fast the chemistry takes place. All right. A lot of that chemistry, though, is strongly driven by ionization. That is to say, we have some ions, not a lot, a small fraction of the gas is ionized in the kind of interstellar gas that we'll be talking about. But the attraction between ions and neutrals is strong enough that a lot of the reactions involved do involve ions. So we do have to consider where the ionization comes from. The kind of chemistry we're talking about is pretty low temperature stuff. So it's essentially room temperature and below very often, but often very much below room temperature. So we may be talking about extremely low temperatures, somewhere on the order of 10 Kelvin is not unusual for an interstellar cloud. What that means then is reactions that are exothermic and or barrierless will tend to dominate. There's not a lot of energy available to drive reactions, and so those reactions that do take place will tend to be ones that can take place readily at low temperature. The pressures also are very low. In many cases, we may be talking about pressures that are so low that they're arguably a vacuum on by Earth standards. That means that, again, because we're relying on collisions for the chemistry, that chemistry is slow. It can take thousands of years for that chemistry to evolve in a meaningful way. Very often, the kind of chemical timescales we're thinking about may be on the order of 1 million years. In an interstellar cloud, that is not unusual. That means that very often, chemical thermodynamic equilibrium is rarely, if ever, reached. So we have abundances that are time dependent. Okay, the time dependence is very important because we don't reach that equilibrium point, and that means we need to consider kinetic models. What that means is thinking about chemical rates. The rates at which things take place as a function of time are important, and so to solve this problem of what is the what do we expect or predict or whatever the chemical abundances of certain species to be, we need to build up a whole network of rates that allows us to build up a collection of differential equations. We then solve those equations as a function of time, and that will tell us those abundances. Right. So the other side of the coin here is the surface and the ice chemistry. So taking place on dust grains or taking place in the ice mantles. There's a lot of chemistry that obviously we'll talk about a bit that goes on there, but some important molecules that are produced on the grains are actually H2, molecular hydrogen, the most abundant molecule. Also a lot of simple hydrides. We detect those. And then complex organics, as we call them, so somewhat more complex molecules, maybe 6 atoms or larger. So far, it's still, the jury is out, I think, on observing those molecules on dust grains, but we sort of expect that they're formed on dust grains. There's a lot of evidence that indicates that they are, and certainly our models tell us that they are as well. But the grain surfaces, I should point out, can behave very differently from the gas phase chemistry, and that a large part of the reason for that is that there's a third body involved. So in the gas phase, it's typically 2 bodies colliding. There's a reaction that follows. On the grains, we've got that third body that can stabilize the products. That means the chemistry that is allowed to take place can be very different. All right, so why would we use astrochemical kinetic models? And I think often in this field, we don't always distinguish that we're talking about kinetics models. So when you hear the word astrochemical modeling, we're usually talking about kinetics models. That is to say, rate-based, time-dependent calculations. So these kinds of models then tell us the time-dependent context of where molecules come from. They tell us also molecular ratios or abundances, and that can tell us about the age and or the physical history of the source. Okay, so maybe, so when I say source, I mean an interstellar cloud or whatever it may be. So we can gain information, perhaps in conjunction with observations that we wouldn't otherwise have. We can sort of look back in time, if you like, using the chemistry, because the chemistry responds to physical conditions that may change with time. We can also use these models to extrapolate or predict the presence of other molecules that perhaps we haven't detected yet. So, you know, we might detect a certain molecule, and we might make predictions about a related molecule based on what our models tell us, and then maybe go out and look for that molecule. Okay. Ultimately, though, you know, certain calculations we can do on paper, and I certainly encourage people to take that kind of simple approach as well. But if we really want to understand the chemical processes that are going on in the interstellar medium, we really don't have an option. We have to use chemical models. They are simply the best way of understanding this whole network of processes that are all going on at the same time. So under what conditions might we actually apply these astrochemical models? Well, there's a whole range of places we might consider. Photon-dominated regions would be one. Related to that are diffuse clouds. As we get to regions that are denser and have a higher visual extinction, that is to say there's more dust in the line of sight, and so we're blocking out more of the external UV invisible light, we'll be talking about dark clouds or dark cores. Once we go beyond that having an interstellar cloud that is dense and dark and actually going to star formation, that's also a regime in which we can model the chemistry. Obviously, there's a large section of the community that are very interested in protoplanetary disks, this sort of somewhat more evolved stage of low mass star formation, where we have molecules that are directly observable in the disks, and we can model that and that's quite a complicated process actually. And then there are also sort of fairly violent regions, so shocked regions, and also regions in extragalactic environments. So most of the astrochemistry, I would say that we typically model tends to be within our own galaxy because it's much closer for one thing. But we can observe chemistry in other galaxies as well. We can apply the same kinds of methods. So the principles that I'll talk about are applicable, broadly speaking, to all of these environments. But I say in general, most of the processes that I talk about are going to be most important for darker regions. So dark clouds, certainly, and certainly the colder stages of star formation. I'm not going to get into protoplanetary disks, but a lot of these processes are still very relevant, and these processes will all be relevant in other galaxies as well. All right, so a bit of sort of mathematical background, because very often when people run these models, it's not very clear, perhaps to them. It wasn't clear to me when I was a starting PhD student. Not necessarily clear what mathematically is being solved. So I wanted to just address that very quickly. So these chemical kinetics models have a set of rates for an entire network of processes. So every reaction or process in that network will have a rate that may be temperature dependent or but from that we can build up a set of time dependent ordinary differential equations, and we integrate them or just solve them with respect to time. And that will give us the abundances that we're looking for. So we have one equation for each chemical species, okay? And we have to solve all of those single equations simultaneously because they are interrelated. So what we do know when we're trying to solve this problem is that at any particular point in time, with any combination of chemical abundances, we can always work out what the rate of change of every chemical abundance in the model is. So we know n dot. So n dot is just dn by dt for some abundance. Okay, so a concentration n. So we always know what the time the rate of change of that abundance of a particular molecule is, because we know we've defined all of the rates in the network. Okay, so that's the known part of it. What we don't know is what the actual abundances are at some projected point in time. Okay, and so that's what we're actually solving. We are integrating dn by dt as a function of time for all of these species simultaneously, so that we get the abundances or concentrations n of all of those species. When we do these calculations, we obviously have a lot of inputs. The most obvious one is the chemical network, and in particular the rates that are associated with that network. So we know the reactants and products, but we also know the rates at which those processes take place. We need to know what the initial abundances are, so the initial chemical conditions, and we need physical conditions. Those physical conditions sometimes are modeled as static, but they may not be. They may be time dependent, so we may have to introduce that as well. All right, so the physical conditions we're often interested in then are gas number density, often just called density, but it has this very special designation, this n subscript h. Okay, and so it's the number density of total hydrogen. I'll get to that in a second. The gas temperature is also going to be crucial for the gas chemistry. Dust temperature will be important for the grain chemistry. We have this quantity called visual extinction. Many of you may know what that means. If you don't, it essentially tells you the degree of attenuation of external UV and visible photons. That attenuation is caused by the dust that is mixed in with the gas. Okay, so it's dust absorption leads to the removal of UV invisible photons. And that means in a dark region, we will have a high visual extinction. And we use units of this A sub V. That's just the sort of astronomical description for that quantity. It's a bit like an optical depth at the visual wave band. So visual extinction is important because, of course, visual waveband and UV photons are able to ionize and photodissociate molecules or to ionize atoms. Okay, so that's why we're interested particularly in UV vis, because we can break up molecules and atoms using those wavelengths. The other big one is cosmic ray, the cosmic ray ionization rate, and I'm sure you've heard about that, but it's essentially charged particles that are very, very energetic, that permeate the galaxy, and occasionally, not very often, but occasionally will collide with something, an atom or molecule or a dust grain. And if it hits an atom or molecule, it'll ionize it or photodissociate it. That's a very important input. And in fact, we're learning, still that not only is it important, but it's probably not a very well constrained quantity either. Okay, so very often when we do modeling, and certainly when people start off doing chemical models, just like I did, we often use dark interstellar clouds as the main example, because they're fairly simple in the sense of they've got a high extinction, visual extinction. There's not a lot of external photons, and they're fairly stable dynamically. That is to say, they survive for millions of years. And so the change in the chemistry, the changing chemical abundances are reflective of the passage of time for the most part, not the passage of external forcing factors like there's a star being formed nearby, or the density and temperature are changing rapidly. It's just time. So very often we use dark interstellar clouds as our sort of typical starting point for interstellar chemistry models, and this TRIX model that I've made available is set up for that. All right, so a little bit more math, and then we'll get on to the chemistry here. So you can, just in a simple sense, if you have a simple ordinary differential equation, you can solve it analytically. An example of this, a very obvious classic example, would be radioactive decay. So you start with a certain amount of some radioactive substance, and you're interested in what it's, how much of it is left after a certain amount of time. Okay, we can describe that system by just saying dN by dt is equal to some rate constant multiplied by the amount of that material that is left. Okay, we can solve that equation without too much trouble, and the solution is that the amount of that species at time t is equal to the starting amount multiplied by some by an exponential that involves a time constant k. Okay, so our solution is an exponential in time for that simple system. Okay, once we get to more complicated systems, it's not easy to do this analytically, and we have to do it computationally. Okay, and so to do that, to get our numerical simulation, we extrapolate n of t over a series of small time steps. Okay, using dN by dt, which is known for under all conditions. Okay, so this picture here is just sort of demonstrating actually Euler's method, which is a very simple kind of crude method of integration to numerically solve an equation. But what you can see is you start off at some time t0. You know what the rate of change is. That's what this straight line is. It's just the slope. Okay, and we can extrapolate the new abundance at some new time t1, where we've got a time step of delta t. Okay, it turns out with this simple Euler's method, it's actually not very effective for anything complicated. What we actually use in practice is a method called Geer's method, Technically speaking, it's what's called a predictor corrector method with backward differentiation. And it's just useful for what we call stiff differential equation problems. That is to say, problems that have a lot of different rates of different values. So there are different time scales involved, so lots of different time constants involved, with lots of species that maybe are highly interconnected. Okay, so this gear method is a very common way of solving these problems, and it's sort of the highest level of solver, I guess you could say, for these types of problems. They can get very, very stiff. Okay, so I noted that the simple solution has an exponential in time. Even in the complex systems, we still see exponential, time-dependent exponentials in the solutions. So if you were to actually analytically try to solve some of these more complicated systems, you'd still see exponentials in time popping out in the solutions. Okay, what that means is that the chemistry generally changes more slowly as time increases. If physical conditions are stable, that means that as a result, it is very common to plot chemical model results as a function of the logarithm of time, okay? Because things start off changing very rapidly, and then they change more slowly over time. So that's why we often plot these things as exponentials. Okay, so let's talk about the chemistry now then. What are we actually solving? So very often people will start off by saying, well, how are molecules formed? Or how is this molecule formed? Where does this molecule come from? That is only half the question, I should point out. The real question we should be asking is, how are molecules formed and destroyed? Those two things have to be always kept in view. The destruction of molecules is equally as important as how they're formed in determining what their abundances are. Okay, so there's a whole bunch of gas phase processes that can either form or destroy one molecule or another, right? You form one molecule, you maybe destroy another one. This is not an exhaustive list, but to put them into some broad categories, we have reactions between neutral species, that might be between two atoms, perhaps, or more likely between atoms or radicals and molecules. We have what we call ion molecule reactions. Again, that can include a whole range of actual types of ion molecule reaction. But the key thing we're really interested in between when we're thinking about neutral versus ion molecule is how quickly do they meet? We find that ion molecule reactions or ion neutral reactions are a bit faster than neutral reactions. And that turns out to be important. When we have ions, of course, they can recombine with electrons, and that is an important thing to consider in our networks. There are photons involved in interstellar space and in these networks. So photoionization and dissociation are important. Cosmic ray induced ionization is important. There are other processes, radiative dissociation and so on. Okay, but it's important to remember, a lot of interstellar chemistry is driven by ionization. That means ion molecule reactions are important. In low extinction regions, you've got UV photons that are driving that. In higher extinction regions or dark regions, cosmic rays are producing those ions, okay? So the photons are now blocked out by the dust, and so we have to rely on cosmic rays to produce those ions that drive the chemistry. All right, so neutral reactions that tend to be a bit slower at 10 Kelvin. It's about a factor of 10, broadly speaking. But those neutral reactions can also be important. Okay, so I'll say something about kinetics more broadly. So most chemical processes in the interstellar medium involve two-body collisions. Okay, we have single atom or single molecule processes. We should be careful not to call them reactions. A reaction involves two chemical species. But if you start with an atom and you ionize it using a photon, that is a single atom process. Okay, so we'll have those in our networks as well. Okay, what we don't typically have is three-body processes. So those kind of three-body processes don't usually occur. The reason is the gas number densities or pressures are just too low. It's very unusual for three bodies all to come together at once. So we don't have to worry about those typically. There are certain regimes, for example, circumstellar envelopes, where the densities are very, very high, and they can become important, but that's not a regime that we'll consider here. All right, so I will give a few definitions. I think it's important to do that. We define what we sometimes call absolute abundance, concentration, or maybe we just say abundance, but we define this quantity that has multiple names for every species in our model, okay, and we call it n, and it's n usually with parentheses around the species, and it has units of particles per cubic centimeter. So in other words, centimeters to the -3. So it's a number density, or the number of particles per unit volume. Okay, that's an important quantity. We often, though, think about fractional abundances. So fractional abundances with respect to hydrogen, because of course hydrogen is the most abundant thing in the interstellar medium. It's the most abundant sort of baryonic material. But what we do is we define it with respect to a particular definition for hydrogen. That is to say, we define it with respect to total hydrogen in whatever form it happens to be, and we give that total hydrogen this N subscript H label. So it's a very special name, this N subscript H. We often call it total hydrogen. It is just the amount of neutral atomic hydrogen plus 2 times the amount of hydrogen atoms that are in molecular hydrogen. If you actually had a lot of hydrogen ions, you would add that in as well. Okay, the key thing is to get the total amount of hydrogen in whatever form it's in. Most of the hydrogen is in these two forms in interstellar clouds, and that means that's typically our definition for total hydrogen. Okay, so that's pretty a pretty accurate calculation. Okay, it's important to do that, to bear that in mind, though. We're not talking about a fraction when we talk about fractional abundances. We're usually not talking about the fraction with respect to, you know, atomic hydrogen, or sometimes we'll do it with respect to this molecular hydrogen, but usually it's the total hydrogen that we're interested in, certainly in the models. All right. For fractional abundances then, I don't know if this is something you've been told in the more observational related classes, but a good rule of thumb is that fractional abundances less than 10 to the -12 can't be observed. Okay, I don't think I know of any observed molecule that has an abundance less than 10 to the -12. For various reasons, that is the case. Okay. Likewise, observations of species with fractional abundances less than about 10 to the -10 are pretty rare. Okay, occasionally you'll get something 10 to the -11, but it's unusual. So that's the kind of range of values we're thinking about. Our abundances of hydrogen, one or the other of these two, will be pretty close to unity for its fractional abundance. Okay, so the abundance of very often molecular hydrogen will be approximately 0.5 with respect to total hydrogen, because almost all the hydrogen is locked up in molecular form. Okay, but we'll have abundances of other species that could go down to, say, 10 to the -10 before they're no longer observable. All right. So if we have a particular reaction in the gas phase, let's just say it's for reaction between A and B, and it produces products C and D, we can have a reaction rate that we can define. That is to say, a total rate. So it will be the number of particles per cubic centimeter produced per second by that reaction. So that's our overall production rate units. Okay, so that production rate will also be equal to the rate of production of species C. It will be equal to the rate of production of species D. It will also be equal to the destruction rate of A and the destruction rate of B. And we can define it like this: some rate coefficient, or sometimes called a rate constant, but if it's dependent on temperature, we tend to call it a rate coefficient, multiplied by the abundance of species A times the abundance or concentration of species B. Okay, so that's a particular reaction. Of course, I define this in terms of n's here, the little n's, but very often we're interested in this fractional value that we often label x. Okay, so if we want to do all of our equations in terms of x, we just have to divide both sides of the equation by n sub h. Okay, so that means that we've got dx by dt. If we want both of these to be in the form of x, we have to multiply by n sub h to do that. I hope that's obvious. So if you divide one of these, you'll end by n sub h, you'll get x here and then n here. So if we want this one to be x as well, we have to multiply it. Okay, so we can't forget that. We have to sort of keep that in mind. Very often, though, that's the calculation that these astrochemical models do. They actually calculate fractional abundances, but it's trivial to do that conversion. All right, so this rate then, for whatever reaction it may be, represents the loss and gain rate for this selection of species just for this reaction. So for one particular reaction. If we want to set up our entire network of reactions, we have to sum up all of those rates for each individual species. So they'll, for species C, okay, it's being formed at this rate, but it will have other reactions that can form it or reactions that can destroy it. If we add up all of those rates together, we'll get a net formation rate, which could actually be negative because it's gradually reducing the abundance of that species. Okay, that will be the quantity that ultimately we're going to integrate. Okay, so that's our total formation or destruction rate, and that's going to lead us to the time-dependent chemical abundance. Okay, so that's all of the math part out of the way, and let's talk about the chemistry side of things. So it's worth considering that there are different stages to gas phase reactions. Okay, and we can essentially break down a reaction into several different stages. Now, this is still, the way I'm going to put this is a little crude, but it is helpful to think of the different stages of a reaction in this way. Okay, so firstly, we should think of the collision. Okay, we're often interested in the collisional rate at which two species come together. That doesn't tell you necessarily what the reaction rate is, but the reaction rate won't be any higher than the rate at which these two things collide. Okay, and in some cases, in many cases actually, reactions will go at the collisional rate. That is to say, as soon as these two things collide, they will react and there's no other impediment. Okay, so the rate at which that happens, of course, is going to depend on the types of species that are colliding, what their masses are, what their charges are, and certain other quantities as well. When they come together, though, we often consider that they will form some kind of a complex or intermediate. It will be short-lived, perhaps, but it will be the intermediate to get to the ultimate products of that reaction. So there are a number of different outcomes. Once you've made your intermediate, you can think of different outcomes that could happen. One would be a successful reaction. That means that you've successfully partitioned the energy, or you've structurally rearranged that intermediate, and now you have products that will separate. What might happen if you don't have a successful reaction, if you don't structurally rearrange things successfully, is you've got something that is essentially scattering, that there's no ultimate reaction going on, and those things will separate again, as we had before. An alternative would be, and I'm not going to get into too much detail on this, but an alternative would be that you could actually emit a photon from that complex, and that would stabilize the product. Okay, and so that is a key concept here, is that when we form an intermediate, it's actually carrying some energy. It's going to be excited, and to stabilize it, to form products or a product, we need to get rid of energy somehow. One way of doing that will be to emit a photon. That's actually pretty hard to do. It doesn't happen usually very often. The way it does happen is that you'll have a rearrangement and then a separation of two products, and those two products will carry a lot of energy away from each other kinetically. So that reaction energy will be transferred into kinetic energy of the products, and that means that ultimately those products will be stable. So we can assign rates to all of these different types of reactions. The way we do that for actual true reactions, two-body collisions and then followed by reaction, the way we do that typically is to use what is often called a modified Arrhenius treatment. Okay, so this is a generalized form that very often is quite accurate in describing the temperature dependent behavior of reactions. Okay, and so what we see here, there's really two parts to this. There's three quantities that define it: alpha, beta, and gamma. There are two parts. The first part is the collisional rate. Okay, so I said that we could break our reaction down into collisional rates and then whatever happens next. Okay, so the collisional rate is the rate at which the stuff comes together. And then if there's an activation energy barrier, we could describe that barrier as a Boltzmann factor this way. Okay, this is an empirical form that actually fits measured data pretty well, and so we use it a lot. Very often, so what we see here is that there's a reference temperature of 300 Kelvin. That's chosen because it's convenient, because 300 Kelvin is room temperature. This beta then is what determines the temperature dependence. Not every reaction will have a temperature dependence. Okay, and if beta is 0, there's no temperature dependence. But usually this beta is somewhere between -1 and 1, and that depends on what type of reaction that we have. So we can measure rates of reaction at different temperature in the lab. We can then fit this to it, or we might do a calculation and get something that looks rather similar to this. And then ultimately, these are all rates that we can put into our networks. Okay, so let's just move on for a second. So let's talk about ion molecule reactions. So many neutral reactions actually do have an activation energy barrier or are endothermic. On the other hand, it turns out that a lot of ion molecule reactions often are not. That's partly to do with the way that the ion and the molecule will be able to orient themselves at larger distances and sort of get into a potential that is that ultimately leads to a reaction without a barrier. Because of that fact that a lot of neutral reactions have barriers or endothermic, and ion molecules reactions are not. In the low temperature conditions we have in the ISM, much of that gas phase chemistry therefore is driven by ionization. Okay, so we'll have let's say some generic ion molecule reaction. So some ion reacting with a molecule, there's some kind of a transfer goes on, and we're left with a new ion and a new neutral. The features of these reactions are that the typical rate coefficients typically on the order of 10 to the -9 cubic centimeters per second. There's a weak temperature dependence, but there are often many exothermic product branches. And again, many of those branches have no activation energy barrier at all. Okay, so where does the ionization come from? You probably heard some stuff about this from other of these lectures. There are different sources. of ionization. At low extinctions, that is to say, in sort of more diffuse or translucent clouds, where there's not enough dust to block out all of the external UV invisible photons that come from ultimately from hot stars, you will have photons doing this job. So just a direct ionization of atoms or molecules can happen. Now, I've stipulated here that our photons of interest are of energies less than 13.6 eV. There is a reason for that, which is that there are effectively no UV invisible photons entering interstellar clouds that have energies above 13.6 eV. The reason is there's a lot of atomic hydrogen in interstellar space that absorbs those higher energy photons. Okay, so those higher energy photons just cannot reach interstellar clouds in general. They will be absorbed around the hot star that produces those higher energy photons. So they're not available when you reach an interstellar cloud. So we don't have to worry about energies above that, but it does mean that there's a very hard threshold as to the availability of ionizing photons. Okay. We can also, at the same time, we can also photodissociate molecules using those same energies of photons. Okay. The other thing that produces the ionization, though, is and this is particularly in high extinction regions where this UV field is very, very weak or non-existent. We rely on cosmic ray ionization. Okay, so direct cosmic ray ionization is one method, and I'll talk about another method in a second. But essentially, we would start very often with H2 because it's the most abundant species in dense clouds. Cosmic ray will hit it, ionize it. Okay, and now we've got an electron, but we've also got an ion that can start the process of ionization chemistry going on in the gas phase. So that's ionization. I'll say something briefly about photodissociation as well. There are a lot of mechanisms by which photodissociation can take place. It is kind of a complicated process, but broadly speaking, it's worth dividing these processes into two. That is to say, some molecules can be dissociated over a whole continuum of frequencies. Okay, other molecules have very specific frequencies or photon energies that are able to dissociate them, and so they're dissociated in lines, as I've said. That's a useful distinction, and certainly for the molecule H2, it turns out to be very important. There are only very specific photon energies that are able to dissociate H2 because it has a very specific photodissociation mechanism. And so H2 does something called self-shielding, and that's something that we have to take into account. In the models, it basically means that once the photons that would photodissociate H2 have been removed, we don't have any other way of photodissociating H2. All right, so you may have heard a bit of about that in the past. If not, I'm not going to go into that any deeper, but I'll talk more broadly briefly about photodissociation. Okay, so photodissociation obviously applies only to molecules, but certainly in these lower extinction regions, it can be an important source of destruction of atoms, of molecules and production of atoms. The rates for this are actually similar to the rates that we have for photoionization. I haven't gone into that here, but the photodissociation rate is described by something that looks a little bit nasty here, but what we're really saying is that there is a range of photon energies that are involved, or frequencies, And we're just dependent on what is the interstellar radiation field strength at all of those frequencies. What is the cross-section of photodissociation as a function of frequency? And then we integrate all of those over all those frequencies. Okay, the intensity of light, of course, is going to depend on the visual extinction. Ultimately, though, what is most useful for models is to have something in this form. So when we see photodissociation or ionization in our networks, this is the form that those rates actually take. It is a prefactor followed by an exponential that really just determines the behavior with respect to the visual extinction. So in other words, if you were to ignore the exponential or you set visual extinction to 0, A would just be the rate of dissociation in the interstellar medium of that particular molecule. Okay, as you get deeper and deeper into your cloud, your visual extinction increases, and exponentially you will remove photons, and therefore that rate will drop off. This B quantity is important because it tells you the relationship between the visual extinction, that is to say, specifically the visual band, and the particular frequencies that are most important for dissociating that molecule. Okay, so the dust will be, the extinction caused by dust will be stronger for higher frequencies than it will be for lower. So we have to correct for that. So that's what that B stands for. So if you were to go ahead and look in that network of the model that I've made available, you'll see some processes that look exactly like this. What you'll see is an A value and a B value, and those are all you need to determine those rates. Okay. The rates then for these processes typically on the order of 10 to the minus 10 to 10 to the minus 9. Note the units, seconds to the minus 1, because this is a single molecule process. All right. I'm just checking on time. So what I think I will do is say something very quickly about cosmic ray ionization, and then I'll talk a bit more about actual molecules and how they're formed through gas phase chemistry, and then we'll do a few questions and answers. So cosmic ray ionization turns out to be very important in dark regions, as I said, because we lose those UV invisible photons that can otherwise ionize atoms or molecules. So the crucial quantity is this, what we call the cosmic ray ionization rate, zeta, or zeta 0 sometimes is sort of used as the canonical value, the label for it. It's not very well determined actually, but it's on the order of 10 to the minus 17 per second. That is to say, it relates specifically to H2 molecules, and we can use that H2 ionization rate as the sort of standard rate that we compare the ionization rates for other species to. So we define it for H2, and then we define for other species the rate in relation to that underlying H2 ionization rate. So this, what we call cosmic ray ionization rate, has a value on the order of 10 to the minus 7. So that would be one H2 molecule is dissociated on average every 10 to the 17th seconds, which seems like a long time, but of course we have a lot of H2 out there, so there is a substantial amount of ionization taking place. Okay, so what happens when that ionization process happens? Okay, well, if you have atomic hydrogen, you'll just ionize it. Okay, if you have molecular hydrogen, there are actually a few things that can take place. The most likely is that you do ionize it, but also you can break it up in various ways. In fact, that cosmic ray ionization rate technically includes all of those processes. Now, the cosmic rays, when this happens, the cosmic rays survive. The cosmic rays really don't feel this interaction very much. The reason is that they have such enormous amounts of energy the average is probably about 100 MeV, mega electron volts of energy, but you can have cosmic rays that go into the GeV territory for sure, and a lot higher. So those cosmic rays actually penetrate fairly easily into molecular clouds, and they actually don't interact very often with anything. So they do penetrate deeply. Okay, so we usually expect that cosmic rays are present in all interstellar environments. They may drop off in extremely dense dark regions, but typically there's enough of them, and they interact so rarely that they can penetrate very effectively. All right, so I should say ionization of helium is also a major source of ions, but in dark clouds, it is this process, this production of H2 plus, that is our main source of ionization, as well as being, one of the main sources, well, the main source of electrons as well. Okay, we can ionize other atoms and molecules with cosmic rays, but because hydrogen is still the most abundant thing there, it's the ionization of hydrogen that is going to dominate in producing the ionization in stellar clouds. So let me just say one thing about the final step in ion molecule chemistry, which is dissociative recombination. So if we have ionization and we have chemistry that leads to different molecules, we've still got ions left over. The final step then, if you like, is when we neutralize the ion and we're left with a neutral molecule. Okay, so what happens when you have a molecule recombining is typically that it is a dissociative process. That is to say, you start with a molecular ion, but because we have a lot of energy released when we recombine with an electron, the product has to break up in some fashion. So you could break up a molecule into multiple pieces, or you could kick off just one atom, perhaps, and that may be enough to stabilize the products. And in fact, that turns out to be a very important process when we can kick off a hydrogen atom from what was an ion. We can end up with a stable neutral product at the end of it. Okay. So the rates for this process, they're a lot faster than ion molecule reactions, of course, because you've got two charges involved rather than one charge and one neutral. So they're fast. But think of dissociative recombination as being the final step in the ion molecule chemistry, this ionization-driven chemistry. So we start very often in dense regions with cosmic ray ionization as the first step, and you ionize things. Then you have ion molecule reactions. Then ultimately, dissociative recombination allows you to return to neutrals that may be stable. So let's talk about, and then we'll briefly stop for a few questions. Let's talk about major formation routes for some simple molecules, at least in the gas phase. All right, so what are the main routes? So as I said, we start with hydrogen. Cosmic ray will hit it, either the atomic or in dense regions, the molecular form, and produce an ion, and we produce our electrons. Crucially, the H2 plus that is produced reacts with neutral H2 to produce H3 plus. So we abstract a hydrogen from neutral H2 and produce H3 plus. This is one of the most crucial reactions in interstellar chemistry because it leads to a lot more chemistry. And in fact, this H2 plus reaction with H2 has a high probability of taking place because once H2 plus is formed, the most likely thing that it will collide with is H2 because there's so much of it. Again, it is the most abundant thing by far, by about 4 orders of magnitude of anything in the gas phase. So H2 is by far the most likely collision partner of any species. So this reaction actually goes very effectively. So ultimately then what we end up with is H plus from this process, and then H3 plus by this very rapid reaction of H2 plus with H2. This turns out to be important. So let's have a look at water production then. We know that there's water in the gas phase. It's hard to detect, but we know it's there through detections, and our networks tell us how it's formed in the gas phase. Okay, it can certainly form on grain surfaces as well by different mechanisms, but in the gas, this is how it's formed. So different mechanisms for forming ultimately OH plus. So OH plus is an important ion on the way to forming water. So either you could have H plus reacts with neutral oxygen. Okay, that's just ends up ionizing your oxygen. Then your ionized oxygen reacts with H2. Again, abstracts a hydrogen from H2. There's a lot of H2 to collide with. An alternative would be if you have that H3 plus that I just talked about, reacts with a neutral oxygen, gives you OH plus. So either of these mechanisms give you OH plus. What then happens? We have reactions with H2 again. Okay, so H2 is a very important molecule, arguably the most important molecule in astrochemistry, because it unlocks a lot of this kind of chemistry. So OH plus reacts with H2. A hydrogen is abstracted from that H2 molecule, and now we've got H2O plus. H2O plus can react with H2 to give us H3O plus. Now H3O plus is protonated water. So it's a water molecule with a proton or an ionized hydrogen atom attached to it. If we're looking to get to water, then what we want to do is recombine this thing, H3O plus, with an electron. Now, that doesn't necessarily always produce water. And in fact, any of these ions could also recombine with an electron and produce something that isn't water. But you can see that if you have H2O plus react with an electron, you can produce OH. Again, it's two products. You don't produce H2O because it's going to be excited H2O, and that energy has to go somewhere. That energy will typically go in breaking up that molecule. So you kick off a hydrogen and you end up with OH. If you have protonated water, you can kick off a hydrogen and still be left with stable water. So in the gas phase, that's our mechanism. So we actually have to go one proton beyond the molecule that we want and then recombine with electrons that allows the hydrogen atom to be kicked off and give you stable water. All right, so you can do similar things for nitrogen. Nitrogen isn't actually easily ionized by photons because, again, we don't have photons higher than 13.6 EV, and nitrogen atom therefore isn't able to be photoionized. It turns out proton transfer from H3 plus actually doesn't go. So cosmic ray ionization of nitrogen is the important thing. So that's how we get the charge into the nitrogen system is cosmic rays. Okay, so we've got N plus. It's possible to do this through other mechanisms as well, but we end up with N plus reacts repetitively with H2. Again, H2 is this really important molecule that allows hydrogenation of these simple species. So we end up with this chain of NH plus, NH2 plus, NH3 plus, NH4 plus protonated ammonia. Then that protonated ammonia can recombine with electrons, kick off a hydrogen. That's not the only outcome that could happen, but that's one of them. And we end up with stable ammonia. Okay, so these are the key species involved at each stage here. So you can see you start with an ion, you then have repetitive reactions with molecular hydrogen, and then recombination. All right, so similar thing for carbon. I don't want to go and labor this too much, but what you can see here, there is a bit of detail involved in some of these steps. So in this case, this CH3 plus H2 reaction doesn't lead to an abstraction. It actually requires a radiative association. It requires a photon to be emitted to stabilize CH5 plus. But ultimately, CH5 plus reacts with an electron, kick off a hydrogen, you end up with methane. Okay, so those are the major routes for those simple hydrides, but we can produce a lot of other species as a result, and not just through ion molecule chemistry, but also through neutral chemistry. So we can form CO in a lot of different ways. So this would be one. If we start with ionized carbon, it can react with OH. If you remember, that was a byproduct of forming water. You get CO plus. CO plus can react with H2 to give protonated CO. Protonated CO can react with an electron to give you carbon monoxide. Carbon monoxide, of course, is one of the most abundant molecules in the galaxy, and a very important one for astronomy. We can form things like the cyanogen radical or hydrogen cyanide. HCN is a molecule we commonly do observe, particularly in star-forming regions. You can also form molecular oxygen. You can form your N2. All of this through neutral reactions involving radicals and atoms. But all these radicals ultimately had to form through reactions involving H2, or at least that's the most effective way of forming them. Okay. So it turns out then H2 is super important in this gas phase chemistry, as you'll see if you run one of these models. I'll also point out there are a lot of mechanisms to form CO, but ultimately they all depend on the presence of H2 in the gas phase, and that's one chemical reason, at least, why CO is a good tracer of H2, is that it's chemically very strongly related to the presence of H2. All right, so this is my summary slide for the gas phase stuff. And maybe I'll just leave that up there and let you ask some questions now, because I know I'm running on a little bit here. So maybe do, I don't know, 5 minutes of questions. Does that work, Sergey? And then
Yes, okay, as you wish. So all students are now encouraged to ask questions in a chat, and we can probably then start with the first question, which has already appeared during your lecture, Rob. So the question is, does number density of hydrogen atoms also include hydrogen locked in water molecules? It was probably related to one of your slides.
yeah, right. So yes, if you wanted to do that calculation exactly right, then yes, it would include all hydrogen in every single form. In practice, we don't actually have to, in the models, we don't actually have to do that sum. So it actually doesn't matter from a technical point of view, because we already know what the total amount of hydrogen is in the system. But this is just the way that we define it. But yes, technically it includes every form of hydrogen. It's just that the amount of water in the interstellar medium is never going to be more than the amount of oxygen that we have in the interstellar medium, and that's about 1 part in 10,000 compared with hydrogen. So it's only a very small change in the sort of precision of that calculation.
Well, they probably still write in some questions, so let me ask you the question about 13.6 eV. So you said that you don't expect those photons at any places, right? But how about H2 region?
Yeah. So well, it's H2 regions where those photons are absorbed. So in interstellar clouds, you do not expect to see those photons. Okay. In the H2 regions that are surrounding your hot star, and every hot star is going to have an H2 region around it in some sense, at whatever size it is, there'll always be enough hydrogen atoms to absorb those 13.6 eV photons. So as soon as once you get to a region where there's an interstellar cloud, then you will you will have absorbed all of those.
Okay, thank you. So then we have a next question. What if a reaction rate for one single abundant rod is missing in a chemical model, and the Arrhenius rate over or underestimates the real rate? How it will change the kinetic results?
Right. So that could be important. I mean, I think the networks are mature enough now that I don't think we're missing any obvious reactions for the commonly observed molecules. Now, of course, I can say that, and it's, you know, it's very difficult to prove a negative for, you know, I think that's the assumption. If we were missing a reaction, yes. I mean, sometimes, you know, people will realize, okay, this reaction might be important. They'll measure the rate, and if it seems high, we'll test it in the chemical models. There isn't really a good answer, you know, a single answer to that. It really depends on the molecule. I think the area where there's the most discussion and the most, well, argument about whether we're missing something is when we're talking about complex molecules. So our classification in astrochemistry is 6 or more atoms, is complex. The smaller ones, I think we've got a pretty good handle on them. When it comes to the larger ones, there's a whole argument about how important gas-phase chemistry is versus grain surface chemistry. There's still a lot of work being done in that area, but there isn't a good blanket, you know, sort of answer to that. It is true on the Arrhenius rate question. It is true that at low temperatures, so maybe below 50 Kelvin, the Arrhenius rates don't always match very well with reality, and that's something that, so there's the group in Rennes in France, for example. He used this Crécy technique. There are other groups, I know it's a UK group and others doing this kind of work, but it allows them to do very low temperature neutral reactions, and they find that for those reactions, at least, you can find reaction rates that are much higher than the Arrhenius rate would predict as temperatures get lower. So in other words, instead of your reactions getting slower and slower with lower and lower temperature, if you had some barrier of some description, as you get to very low temperatures, you may find that barrier seems to disappear, or in other words, quantum mechanical effects start to take over, and you're able to overcome that barrier by some other means. So the rates can actually approach the collisional rate as you get to around 10 Kelvin. That is true, and I think that's the importance of people doing these measurements in the lab. Yeah.
Okay, thank you. Yeah, just another short question from me. So how important is the computation power? So, for example, if our computer would be, let's say, millions times more powerful, would it allow you to do any better calculation, or the limit not with computers nowadays?
So if we had infinite computing power, yes, we could do a lot better. As I'll show you in a second, actually, it's the grain surface chemistry that is the real challenge computationally now. That's not to say, you know, if we want to do a very complicated physical calculation where we've got some region like a star forming core or something, and we want a lot of spatial information, that means we have to run a lot these models over and over again, and you know, for all those positions. In that case, yes, there will be a computational cost, but it's really the grain surface chemistry where there are a lot more calculations that ideally we would be able to do, but we're limited by computational power. But frankly, I mean, I think that the incremental changes that we see in computational power are not going to lead to some kind of enormous leap in our ability to model astrochemistry. You know, the limitations in grain surface calculations are often many orders of magnitude that we're talking about, where we go. Well, I'll talk about that in a second, I guess.
Okay, thank you. Then I'm waiting for your next part of the lecture.
Yes. All right. I'll go ahead.
Okay.
Okay. So yes. So grain surface chemistry. All right. So I hope I've given you at least a very basic idea of what goes on in the gas phase. And again, there's a lot of chemistry you can't get into, you know, in such a short time. But I'll say something about the grain surface chemistry, give you a few definitions and so on. Okay, so I should say something about dust grains first, which I will do. I will describe some, well, different types of gas grain model. I'll talk about the different processes and the way we get the rates. And then I'll say something about diffusive reactions, and then the newer part, which is non-diffusive reactions, which is something that my group has been working on a lot, trying to sort of characterize in the models. And then I'll sort of go over these briefly, these pitfalls for models. All right, so gas phase chemistry models are often very good for certain types of environment, but I think we've begun to learn over the past few decades actually that chemistry that takes place on interstellar grains is also important, and it's especially important, I think, for regions that start cold and get hot. That is to say, when you have star formation taking place, and that's often where we see the most complex molecules is in star forming regions. And it probably is because we have dust grains that start off cold. We have a lot of chemistry going on those grains. Then as we heat them up, as the star forms, those molecules are desorbed from the grains, and we see the results of the chemistry of that was taking place on the grains. So I can say something about interstellar dust grains, and this picture is an interplanetary dust grain. So it's not a real interstellar dust grain. In fact, you can collect interplanetary dust grains from the upper atmosphere of the Earth, and this is an example of this. This picture doesn't have a size scale, but it's probably on the order of about 10 micron from end to end, perhaps a little larger. Interstellar grains are probably about the size of, you know, one of these small sort of nodules that makes up this whole larger structure. So this interplanetary dust grain is a coagulation of smaller, what we would think of typical interstellar grains. So the canonical size distribution could be substantially less than a tenth of a micron, maybe a hundredth of a micron. We often think of a typical grain as interstellar grain as being about 0.1 micron. And implicitly or explicitly, we usually consider the grains to be spherical. In reality, they're probably somewhat off spherical, somewhat prolate is likely. In terms of mass, dust grains make up about 1% of the mass of an interstellar cloud. So they're not an enormous fraction of the mass. But of course, they are important for various reasons, such as they block out UV invisible light from outside, and they serve as a meeting point for atoms and molecules from the gas to do other types of chemistry. So a 1% fraction by mass turns out to be, in terms of number, assuming you have a single grain size, what a 0.1 micron grain, that means that you have about 1 grain per 10 to the 12th gas particles. And so that's a number that's worth bearing in mind, as is this 0.1 micron, our typical, well, radius for a grain. So let me say something about types of gas grain model. And so this is the label that we use for models that do not just the gas phase chemistry, but the grain surface chemistry, and that couples them together in some sense. The simplest way that you could do a gas grain model is to have what we call a freeze out only model. And the names I've given here are somewhat my terminology, that they're not always very well labeled actually, or just don't have a sort of a formal name. But This would be a gas phase model that includes accretion terms, that is to say adsorption. If you're a chemist, in astronomy and astrochemistry, often we'll use those terms interchangeably. So accretion of material onto the grains is the same as adsorption. And very often we'll also use the term freeze out. That is to say, this often happens at low temperatures. And so gas phase material will freeze out of the gas by sticking to the cold grains. And it will typically stay there. Most of that material will stay on the grains at those low temperatures. Okay, so a gas phase model with just that accretion process, that would be a good starting point. But it's not really modeling the chemistry on the grains. All it's doing is removing material from the gas phase so that it's not able to react in any way in the gas. Very often these types of models will include H2 formation on grains. And as we'll see, and I didn't really mention this in the first part of my talk here, but almost all of the H2 on net that we have in the interstellar medium is formed on grain surfaces, which makes it even more interesting that it's such an important gas phase molecule, and yet to form it, to bring two hydrogen atoms together and produce molecular hydrogen, you need a grain surface to do that efficiently. So very often these models will include, okay, accretion of stuff from the gas onto the grain, and it just removes it from the gas and nothing else happens. And then maybe there's a simple H2 formation rate involved as well. All right, it's possible to do a model that goes a step beyond this, where we could call it a quasi-grain surface chemistry. That is to say, we have all the usual gas phase chemistry. That's all properly treated. But when we have accretion of gas phase material onto the grains, we maybe make an assumption about what the form of that material will become. That is to say, if you have oxygen atoms from the gas that stick to a grain, we'll assume that they're going to be producing water. That's typically the most likely outcome, is that you'll produce water. So in your model, you might just say every time an oxygen atom sticks to the grain, let's call it water on the grain. You could do something similar for CO, for example, but we know CO will form different products. Sometimes it will stay as CO, sometimes it will form CO2, some of it will form formaldehyde, some will form methanol. Okay, so in a simple model, you might just make an assumption, an empirical decision as to what the form of that stuff might be, so based on observations. Okay, and we've got a model now that at least crudely tells us how much of these molecules we have on the grains. This is a method that has been used, a fair amount in the past. Maybe a couple of decades ago was common. I think before there were a lot of people doing explicit chemical treatments on the grains. This is actually the method that this tricks code uses. So this is the model that I've made available to you on my website. So if you run that model, you will find that you do freeze out material from the gas phase, and you do form certain molecules on the grain surfaces. The real gas grain models, though, start with what we would call a two-phase model. That is to say, a gas phase chemistry and a grain surface chemistry. And you would couple those through various processes. That would mean accretion of stuff from the gas onto the grain. And then there'll be thermal or non-thermal mechanisms to get atoms and molecules off the grains back into the gas phase. And there have been a lot of models that have done things of this nature through the years, but this Hasegawa and Herbst 1992, or in fact, I think it's Hasegawa, Herbst and Lung, actually, I mislabeled that, but they did several papers in the 90s, and but their papers were particularly influential and I would say comprehensive in the way they treated the chemistry. If we were to go beyond this, and I think this is more the state of the art now, is three-phase models. So a three-phase model is like a two-phase model, and says, okay, it still has gas phase, still has surface chemistry, but it allows the surface of the material that is being formed. So in other words, you have a grain with ice on the surface that is partially formed of water, but other molecules too. Okay, but you're forming this icy material, and it allows you to model the surface of that material as well as the bulk material beneath the surface. Okay, and it's a little bit more complicated of a numerical treatment. Very often, at least the earlier three-phase models didn't consider any chemistry in that bulk ice below the surface. More recent models do that. They include, in particular, my magical model includes movement of certain reactants within the bulk ice, as well as what we call non-diffusive chemistry as well. So we have a chemically active bulk ice in that case as well. Okay, so there are variations of all these different models. It's possible to model chemistry on multiple grain sizes all at the same time. It becomes very complicated. My own experience is that it's probably not worth the effort. I guess, Sergey, your question about if we had, an infinite amount of computing time, well, I guess we could do that. We could do multiple grain size calculations within these models more easily. But it doesn't make an enormous difference. And I think that's why that kind of model hasn't really taken off that much. So these are all what we would call rate-based models, or they're based on differential equations. Just like what I talked about with the gas phase, we can set up differential equations that will govern the grain surface chemistry as well. There's a different type of model that has become more popular recently that is useful, has very particular uses, but is quite expensive computationally. And that is what we call kinetic Monte Carlo models. And again, there are different types of this kind of model as well. But broadly speaking, these, or at least the microscopic kinetic Monte Carlo models, what they do is they follow the position of every atom and molecule on the grain. Okay, so rather than having just a concentration, so that you know how much atomic hydrogen there is at a particular time in the model, how much atomic hydrogen there is on the grain, or you know how much molecular hydrogen there is on the grain, or CO molecules or whatever. We know how many there are and where they are in relation to each other. Okay, and what that means is that we can simulate the chemistry very accurately. What it does, though, is that it makes it much more complicated, because now, instead of having one quantity, the abundance that you have to follow, you now have maybe 1 million atoms and molecules at least on a typical size grain that you have to track. Okay, and so you've got lots more variables. You've got to do every possible thing that every atom or molecule could do, not just that whole population. So that turns out to be quite important. Often these models don't include gas phase chemistry because they don't use differential equations. So they have it becomes a little more difficult to do gas phase chemistry, but it can be done. I can say that for sure, because we've done it in my group. I should mention something about what we know about solid phase molecules, because ultimately, when we do gas grain chemical simulations, that is the products of that chemistry are mostly going to remain on the grains unless we substantially heat up those grains and release the molecules into the gas phase, which certainly happens. Most of those products are going to stay on the grain. So what do we know about the products of grain surface chemistry? Well, we can observe molecules in the solid phase in the interstellar medium. We do that through infrared absorption spectroscopy, and you may have heard more about that in other classes, or you may have that to come, I don't remember. Typically, we see small molecules. Okay, so we find vibrational spectra for molecules observed in absorption against a field star. There's just some random background star behind the cloud. Or it may be that if you're looking towards a protostar that is surrounded by an envelope, that protostar will emit enough infrared that it can be used as a background source, and then we observe absorption against that background. And what we see then is simple molecules, very often simple hydrides. So lots of water. So everything here in this table is in relation to water. But water isn't everything in the ice. In fact, it's probably around half of the molecules in the ice mantles that form on the dust grains. The other major components are CO and CO2. They can have polar and non-polar components. That means they have varying degrees of mixing with water, which is a polar ice. Or they may just mix with themselves. They may self-segregate into CO regions, or CO and CO2 rich regions. We also have smaller amounts of other hydrides, so methane, not always detected in every source. Methanol certainly, and in fact, methanol abundances can get as high as about 30% with respect to water, and a few other things. Now with James Webb, we're starting to see hints that there are more complex molecules present as well, which is sort of what we expect. That said, I would warn you that those observations are very difficult to interpret because the spectra is so complicated. So while I think it's very likely there are more complex molecules than these on the grains, there's still doubt as to whether we're really definitively detecting them at present using James Webb. But I'll leave that as a, to leave that hanging out there. Okay, so what do we have going on the grain surfaces then? So there are essentially two main sort of obvious mechanisms that can take place on dust grains for chemistry to happen. So if we imagine just hydrogen atoms sticking or accreting or adsorbing onto a dust grain, there are two ways in which we could make H2 from those two hydrogen molecules. Okay, and so the first one is what we call the Langmuir-Hinshelwood mechanism. That's a physical chemistry term, but it just describes a case where you have reactants on a surface and they diffuse on that surface until they meet, and then they can react. Okay, so we adsorb first, and then we have thermal diffusion or hopping. So what happens is these atoms will hop from one local binding site on the surface to another, and then randomly, occasionally, they will meet. And when they meet, they can react. And in fact, because they have this third body present, the grain, the energy that's produced when those atoms are brought together can be absorbed by that grain and therefore stabilize the product. So on grain surfaces, it's very much easier to bring together two reactive things and produce one product. Doing that in the gas phase is very, very unusual because we have that excess energy that doesn't have anywhere to go. So either it rarely will emit a photon or the product will break up in some fashion. Okay. All right. In the case of H2, very often that H2 molecule will rapidly desorb. It may hop around a few times, or it may immediately desorb into the gas phase. So that's one mechanism. The alternative is called the Ely-Rideal mechanism, which again is another physical chemistry term, but it's sometimes called the prompt mechanism. And it essentially means a case where you have one atom, in this case, on the surface in a particular place, and the other atom comes along and just hits it directly, essentially just lands on top and reacts with it. Most models, actually, interstellar chemistry models, don't consider Ely-Rideal because it actually tends not to be very important. In most cases, it's not important because the number of target particles, in this case atoms, on the surface is usually fairly small. For Ely-Rideal to be important, you need a high coverage. You would need to have lots of hydrogen atoms all over the grain to have a high probability of that Ely-Rideal mechanism taking place. What's most likely is that two hydrogen atoms, when they hit, will hit in different places on the grain, and then they meet by a fairly rapid process of diffusion. So usually we ignore the Ely-Rideal process. Turns out, I think more recently, there are certain cases, certain types of reaction where ED-radial may be important. All right, so let's look at water. So it shows you how water could form in the gas phase, and it involved ions, repetitive hydrogen abstractions from H2, and then recombination. It's much more simple, or at least we have certainly much simpler processes available on the grain surfaces to form water. And in fact, grain surfaces are where we find most water when we do observations. You know, if we can compare gas phase and grain surface, a large fraction of the oxygen budget in an interstellar region will often end up in grain surface water that is formed on the grains. And so this would be the process. Okay, it's a diffusive process, and in this case we start off, okay, we've got an oxygen atom sticks to the grain, a hydrogen atom sticks as well, and then the hydrogen atom hops around the surface. Maybe the oxygen hops occasionally, but it's more strongly bound to the surface, so that's less likely. But eventually the hydrogen and the oxygen will meet and produce OH. Okay, then that process will happen again. Another hydrogen will come down and react and will form water. That water will typically stick to the surface. There's a small probability that it will leave, but in general, water is going to be much more strongly bound to the grains, and so it will remain. So the key takeaways then, that grain absorbs most of the excess energy from the reaction. So our atomic addition reactions are going to happen much more easily on grains. That means that the grain surface chemistry is very different from gas phase chemistry. It's not just a different place where it's taking place. We have a whole range of alternative reactions that are just not efficient in the gas phase that are on the grains. All right, so what I want to show you next is a simulation of this process. It's a fairly simple model that I produced about 10 years ago. This model is called Mimic. This code is called Mimic. And what we did, at least in this model, was to start off with a very simple approximation to a dust grain. So it's a very regularized dust grain, and it's essentially spherical. And what we'll see here is where a hydrogen atom or hydrogen atoms are moving around on the surface and are going to meet an oxygen atom and form a water molecule. Okay, so this is an example of that microscopic Monte Carlo kinetic simulation method, where we simulate the positions of every atom and molecule at all times. Okay, so let's start the video here. Okay, so the rotation of the grain is just for aesthetic reasons, so that doesn't matter. You can see, okay, where it is. All right, there's a hydrogen atom moving around. It's just randomly hopping around on the surface. And eventually it's going to meet that OH radical that was just formed. And then you'll end up with another water molecule on the surface. Here it comes. There we go. Okay. So we just formed water. And if you do that lots of times, of course, then you can produce a whole ice mantle. And so this is what happens if you run that simulation for a long time. This is obviously a different way of doing a time lapse on this. So we're not seeing diffusion now. There's a whole load of diffusion processes that we're not seeing. But we're gradually seeing the buildup of the ice. The camera in this case is gradually panning backwards. That's why the thing sort of seems to stay the same size. Okay, but what you see is an amorphous looking grain that actually has some crevices in there as the ice builds up. Also, you see there's those blue molecules in there. They're colored blue to sort of aid the eye, but they're actually molecular hydrogen molecules. So what you see is molecular hydrogen, although it's actually a fairly mobile species even on cold grains. It likes to get stuck in those crevices and in the little sort of nooks and crannies within that structure. So it turns out that simulating microscopically exact ices is important because you can get these trapping effects where it depends on the structure of the ice that you're forming as to what these molecules are doing, right? So you're seeing a trapping of molecular hydrogen in that structure that you wouldn't get if you did just a rate-based simulation. All right, so let me show you a slightly more complicated version of this. This is, again, the MIMIC model. And now we've got not just water and molecular hydrogen forming, but a whole bunch of other species as well, simple hydrides mostly. And we're doing this on a larger grain. And okay, we're still seeing the same sort of behavior. We've got a fairly amorphous type of ice springing up. Of course, you know, the structure of the ice as it forms is dependent on the diffusion of all of these atoms around the surface, even before they form molecules. So what in fact happens is that when you have an oxygen atom land on the surface, it's relatively mobile. It can move around. And so the amount of moving it does on the surface is important, because once it gets hydrogenated, it will form an OH radical that will be much more strongly bound to that polar water surface, and it will get stuck. So the longer period you have for your oxygens to move around, the smoother of an ice you will tend to get. If the oxygen is immediately hydrogenated as soon as it lands, and it doesn't get to move very much, then you're just going to get ices forming essentially wherever the atoms land. If they have time to move around first, they can find stronger binding sites. They can fill in those gaps. And so you tend to get a smoother ice. So there's a whole lot of effects that we get from this kind of simulation that we don't otherwise see in a regular gas grain model. So this is what you see: different temperature structures, different temperature models producing different ice structures. So the smoother ones tend to be the ones with longer periods of diffusion for oxygen in particular. Okay, right. So let's consider, you know, can we use these complicated systems for most environments? Unfortunately, the answer is no. That these methods are so expensive that we just cannot do. In fact, we can't typically go much beyond 10 Kelvin for these kinds of simulations because we have so much diffusion going on. We have to model every single diffusion process. Okay, so this is ultimately what we tend to do. We will tend to use rate-based models when we have to go to high temperatures, like you see here. We're going up to, say, 200 Kelvin. And what we're seeing here is these dots are the solid phase water. And then once you get to a high temperature around 100 Kelvin, that water desorbs, goes into the gas phase. Okay. So this kind of rate-based model then, using differential equations for our balances, we don't get that structural information. What it is good for, though, is complicated chemical networks or complicated models or models with complicated gas dynamics and things of that nature. All right. So what are the key processes that take place on grain surfaces then? Those are adsorption, desorption, diffusion, and then reaction. And that reaction will tend to happen when diffusion brings things together. And so that's the key process that we are very often most interested in when we want to formulate the rate at which a reaction takes place. And so when we formulate these quantities, the key thing is the diffusion rate of a certain species. So some species I, it may be a hydrogen atom, has a rate of diffusion, and that rate of diffusion corresponds to the rate at which an atom hops from one site to another, like we saw in that microscopic, you know, the video of the microscopic Monte Carlo model, you saw that hydrogen atoms hopping around from one site to another, one adjacent site to the next. We can define that in a rate-based treatment using some generic barrier, okay, and we can work out what that diffusion rate is. Okay. We can then formulate a reaction rate from that. So we can say for every hop that takes place, for every time a hydrogen atom on the surface hops, what's the probability that its reaction partner is there waiting for it in that site that it just jumped into? Okay. And so that probability will be the abundance, the number in this case, the big N here is just the count of, let's say, oxygen atoms, divided by the count of possible sites where that oxygen could exist, the number of surface sites. Typically, we have about 1 million surface sites on a 0.1 micron sized grain. So that's the probability. If we know how much oxygen there is, let's say, and we know how many sites there are, which we do, we know what the probability is of a hydrogen atom meeting an oxygen atom every time it does a hop. Okay, that means that the diffusive meeting rate for species I hopping to species J is just this. It's the hopping rate times the abundance of species I times the abundance of species J divided by the number of sites. Okay, so that's the way we formulate it. In practice, we need two of these terms because species J, your oxygen, or maybe it's another hydrogen, also is hopping around on the surface. So we just add the two terms together. There's a rate for each of the hopping species. And we end up with an overall rate that is actually doesn't look too much different from a gas phase rate. Okay, so you have a reaction rate that is ultimately based on the diffusion rate, the number of sites, but it depends also on the abundance of I, the abundance of J. Again, in this case, these are populations, the count of atoms rather than the concentration. Okay, so, all right, we could ask the question, so this is in the rate-based treatment. We could ask a question, how do Monte Carlo models do all this? Broadly speaking, they do it in the same way, except every atom or molecule has its own position. Every hop or process of any kind is modeled individually, so not through a reaction rate that applies to the entire population, but to that one atom or molecule. It also means that we have local conditions can be taken into account. So we may have a local binding site that is strong versus a local binding site that is weak. We can't distinguish those in the rate-based method, but in Monte Carlo models we can. That means, though, that again, this hop by hop treatment for the diffusion rates is very slow because we have to model every hop instead of population level reaction rates. Okay, we still have inconsistencies or difficulties in Monte Carlo models. For example, we have to make a big approximation about H2 when we're talking about kinetic Monte Carlo. We don't allow it to accrete onto the grains. That's the typical way we do that. The reason we do that is that there is so much H2 in the gas phase that it dominates the model. In other words, it makes it so that you have so many calculations to do that you just cannot get to the end of your calculation. Because what happens is H2, it's sort of 10,000 times more abundant than anything else in the model. And what will happen is it will stick to the grain, hop around a few times, and then thermally desorb. Nothing much has happened, but it has wasted your time. Okay, and so we have to sort of rule that out. So what that means is, although these Monte Carlo models are very useful in their way, they also don't tell the whole story. Okay, if again we had infinite computing power, we would include H2 diffusion and everything on the surface, but we can't do that. Okay, so there are limitations even to these very complicated models. All right, so let me just finally say a few things about how we form simple ices in terms of reactions. So the reactants adsorb from the gas phase. Reaction rates are mostly driven by hydrogen diffusion, okay, sometimes H2 diffusion. And even in the Monte Carlo models, we form H2 on the grains. We just don't adsorb it from the gas, okay? But it's much simpler to form these hydrides. So I talked before, it was ion molecule chemistry that was driving the formation of methane. Here we just repetitively add hydrogen to carbon. That's how you form methane. For ammonia, you just repetitively add hydrogen to nitrogen. And there's a couple of alternatives for water. In fact, it's a little bit more complicated. There are other reactions that can happen, but broadly speaking, hydrogen addition to oxygen is good enough to produce pretty much all the water on interstellar dust grains. You can also form CO2. That was a bit of a question for a while, but I think most likely it is this CO plus OH reaction. There is a barrier involved. I guess this should actually kick out the hydrogen. I guess this is not strictly a correct reaction. And for methanol, again, this is a series of reactions, but it's essentially just hydrogen addition to CO all the way through to formaldehyde, and then you continue to add hydrogen to get to methanol. So I'll say something quickly about what we call non-diffusive reactions. And one of the issues has been we've noted that it seems to be possible both in the lab and in fact in the interstellar medium to form what we think of as complex organics, even at very low temperatures. Now, why would that be a problem for grain surface chemistry models as I've just described them? Well, the reason is that when you have large radicals that might recombine to form an even larger, what we call complex molecule, the diffusion rate is very slow. These two things are very strongly bound to the surface of a grain or to the ice. And so what's most likely is that hydrogen will come along and react with one of these two radicals, and they're gone, and you're not going to form a complex organic. What was missing from our models was the possibility, though, that you could form one or other of these in the presence of the other. That is to say, grain surface chemistry could produce radicals next to other radicals so that they didn't have to diffuse. So they would immediately be next to each other and react. And that would mean that you could form a more complex molecule. So an example would be this, what we call a three-body reaction. So you have an initiating reaction where you hydrogenate CO that happens to be next to a methyl radical. Hydrogen diffuses, produces HCO, but neither the HCO or the methyl radical have to move. One just has to be formed next to the other. To save a bit of time, I'm not going to go into that in any more detail, but I will just point out that we're now seeing that these non-diffusive processes, that is to say where there's maybe some diffusive process prior, but the actual reaction we're interested in is not driven by diffusion, but driven by the production of one or other of those reactants next to each other. We're finding that is a very important process. That's something that the rate-based models have missed, whereas the microscopic Monte Carlo models naturally reproduce this behavior. We just tend not to use those models very much for complex molecules because the physical conditions tend to be very complicated when we see those molecules. All right, so a quick summary, and I know we're getting very close to the end, so I'll finish up. So, all right, so our summary on grain surface chemistry. Again, the model that I've given you or made available to you doesn't really include any proper surface chemistry, but in reality, diffusive reactions are going to build up most simple species. We're now seeing that non-diffusive reactions seem to be capable of producing larger molecules, even without that diffusion. And so as a result, we're actually seeing the complex organic molecules that we often thought of as being particularly associated with warm or hot regions of the ISM, like star-forming regions, and they still are associated with them, but it seems to be that those complex organics are actually forming much earlier than we thought, during that very cold period when there's a buildup of the ices of all kinds. That is to say, around the same time that methanol is being produced on the grains, we think that a lot of other complex organics are forming as well. So that could be happening also in dark clouds and other dark regions where we don't traditionally see complex molecules because they're still cold regions, and so we expect those molecules to still be stuck on the grains. Okay, but it may be possible. So let me say briefly then, my final slide, what are the pitfalls, limitations of chemical models? So as we had a question just now, I'm sure there are missing gas phase reactions, but the approach that we take to gas phase chemical modeling is pretty reliable. I think for simple molecules, we probably do have mostly fairly accurate networks at this point. The biggest problems do come with grain surface and ice chemistry. Some of that's because there's a lot that we don't know, or there are complications to actually simulating it. But also some models just don't do a very good job of grain surface chemistry. They're not perhaps very up to date. That's just a function of the field, I guess. But you get people who do mainly gas phase chemistry and have a model that has only a very crude grain surface chemistry involved. You have to pay attention to what the models are doing. Okay, it does seem that this diffusive chemistry doesn't explain everything. Non-diffusive mechanisms are starting to become important. I didn't talk about this, but there are other issues, stochastic problems that can be solved with Monte Carlo models, but you have to be careful of with rate-based models. And that structure of the ice is difficult to model with differential equations. Okay, it's not obvious to me that we're going to be in a position to model ice structure very effectively for all physical conditions for some time, just because it is such a technical challenge to do it under varied physical conditions. Okay, there's a lot of lab data also that we have for quite complicated reaction mechanisms and photoprocessing and so on, that although we have good lab data, it's not obvious how to model it explicitly because the systems are so complicated. So we have to be careful about that also, about necessarily expecting lab results to be exactly the same in the interstellar medium as they are in the lab, without actually doing models that can allow us to extrapolate that. So I would point out, as a modeler, there are no perfect models of gas grain or complex organic molecule chemistry. You do have to be aware of what the models are doing. So I guess I'll leave it with that. A warning: be very careful of astrochemical models. All right, let's stop there, I guess, and do some questions.
Okay. Thank you, Rob, for this very interesting lecture. And yeah, we will start now with a question session. So please, everybody, ask your question in the chat. And yeah, we have already a few of them.
Mm-hmm.
So, first question. Could you please explain reaction on ISM and reaction in ISM?
I think that's just perhaps that's a mishearing of my words.
Ice. I guess
so yeah. Oh, so is it ice? So yeah.
It's written ISM, but I would probably guess regarding ice. But yeah,
okay,
written ISM.
So if you had so if we were thinking about reactions on the surface of ice versus in the bulk ice, is that, I guess that's what we mean. So reactions on the surface are going to be different. We have a different method of diffusion. So hydrogen and other atoms or molecules on a surface are able to do this hopping process between local binding sites. In other words, potential minima on the surface. And that's how they can move and meet and therefore react. In the bulk ice, reactions are likely to be much more restricted. I think it's likely that, and it's not entirely well described, that hydrogen can move, either hydrogen atoms or molecules can migrate within the ice. There's some lab evidence of this happening, essentially because they're very small and light. But larger species are not going to be able to move. They're probably going to be locked in place. There may be some local rearrangements going on within the bulk ice. Where the chemistry is most likely to be taking place in the interstellar medium in the bulk ice is when you have photons penetrating the ice, causing dissociation of molecules. And as a result, you may have other species nearby that those photoproducts can immediately react with. Or you may just kick off a hydrogen, for example, and that hydrogen can escape through the ice. And as a result, you may have chemistry elsewhere in the ice because that hydrogen attacks something. So it is quite a different behavior, whether it's on the surface of the ice or inside it.
Okay, thank you. So the next question. Could you please explain the mechanisms that drive ice mixing on dust grain? Shouldn't there be a distinct mantles of different species in layers? Is mixing a result of intermittent thermal processing or something else?
Okay, yeah. So there's evidence of mixed ices, microscopically mixed ices, and there's evidence of ices that are segregated, as you could say. Some of that is, for example, you can see that there are CO and CO2 polar and apolar signatures. So sometimes those molecules will be well mixed with water ice. Other times they'll be segregated amongst themselves. It's not entirely clear why that does happen. Ultimately, there is diffusion going on of those molecules, and there will be different degrees of or different strengths of binding between different types of molecule. Water bonding is going to be very strong, and in general, anything that is able to accept or donate a hydrogen bond is going to be quite strongly bound to water. It may indeed be the case that some degree of physical processing, that is to say, either heating or perhaps photoprocessing, is necessary to drive some of the segregation. So you might have, for example, a relatively elevated temperatures to which CO starts to become maybe mobile, maybe it's driven out of crevices within the ice. That may be a way of doing it. We also have to consider the structure, in the sense of you may have a porous structure made of water that could trap ices. And in fact, that's something that is done often in the lab, is that you produce a porous water ice and then deposit something relatively volatile like CO, and you'll get trapping and segregation of CO within those little pore structures. So that's another way that could happen. I mean, it's a broad question, and it does depend on the environment that we're talking about, and lots of other things. But it's an interesting question for sure.
Thank you. The next question is partly related to the previous one, and it is, what causes diffusion of adsorbed molecules on ice grain surfaces?
Okay, so it is. So if you imagine that we're mostly talking about what we call physisorption, which is to say something along the lines of a van der Waals type interaction between a molecule and the surface. Okay, and obviously that the type of interaction will depend a little bit on what that surface is, but it's a physical interaction. Okay, and so when we have binding of a molecule on a surface like that, it is bound into a local potential minimum. Okay, and so that you can imagine a potential minimum that is sort of rippling away off into the distance. So in some direction or other, from the viewpoint of that molecule, there's going to be a saddle point. There'll be some lower, sort of part of that local potential through which that molecule could pass. The way that happens then is through one of two mechanisms, either a thermal process or a tunneling process. Typically, we think that tunneling isn't very important for surface diffusion. The reason for that is that the distance between binding sites is likely quite large, probably too large for tunneling to be important. So if we just, for the sake of argument, ignore tunneling, we're mainly talking about thermal diffusion then. And that means that you've basically got your molecule sitting in that binding site, and just through a random process, there will be occasional vibrational knocks that molecule will take, just because you've got a dust grain or an ice with at a certain temperature, and there'll be slight fluctuations in vibrational energy over time. And occasionally your molecule will get a bump, and it will get enough energy that it will be able to overcome the barrier between the binding site that it's in and the next one. I hope that sort of makes sense.
Okay, thank you. So the next question, can the MC method estimate feed the rate coefficients of some reactions so that we can use this result to refine the chemical network in rate equation method?
Yes. I'm trying to think of a good example of that. I mean, often when we use the Monte Carlo method, it's as a way of testing reactions, or perhaps a small network of reactions under fairly controlled conditions, with the understanding that because we're using a microscopic method, we don't have all of the inconsistencies or inaccuracies that we would have in a rate-based method, because we're basically treating every atom or molecule individually. So we can get proper statistics. We're not going to have stochastic inaccuracies. And so it's a good way of testing estimates. Is it a way of estimating? Well, yes, in a sense, I guess. I mean, this is a very broad topic, so I can't really cover it all. But I guess yes, it can. I think that's the easiest way of putting it.
Okay, thank you. The next question. How can we use ionization-driven processes and grain surface chemistry as a tool to study the chemistry and physics of potential astrobiological environments in laboratories and computer simulation, with actual and possible new technology like quantum computing and artificial intelligence?
Okay, there's a lot in there.
Yes.
How can we use it? Well, I think okay, the way I will address this is in two parts. So I think we don't do enough as a field, we don't do enough work trying to reproduce lab environments accurately. There is a lot of lab data and experiments that are done really well, and we often just sort of make approximations or sort of draw out in a non-modeling way rates of reaction, so on, and then just go ahead and apply them to interstellar models. I think it's worth our while spending more time trying to model actual experiments. A lot of those experiments do involve sort of astrobiological questions, at least. So forming complex organic molecules in ices. This is something that Sergey does as well. I think so. Yeah, I think it would be good to model more of that. What can we do with quantum computing and AI? Okay, quantum computing is a whole other question, and I'm not sure that we're anywhere close to being able to use quantum computing in a meaningful way for this kind of scientific research. Quantum computing is in its infancy, and there's even among experts there's a lot of, I would say, skepticism as to what it can produce in practice. So I wouldn't hold your breath for quantum computing. What can AI do? I think there's a lot of room for that. I think there are a lot of things that we as chemical modelers do that we don't necessarily have to do anymore if we get AI to do it for us. I still think it's true, though, that this famous phrase of garbage in, garbage out is still true. I'm not necessarily convinced that AI is the answer to everyone's problems. AI does a very good job at sorting through a large amount of data and finding trends, and I think that's where it can be useful. running large numbers of models and drawing out information from it. And that may actually be very useful for modeling lab studies as a way of teasing out reaction rates from complicated lab experiments by modeling those experiments and using iterative processes to model them, and then use AI to draw out those trends.
Okay, thank you. So the next question, is there any evidence or possibility of ions getting adsorbed on ice grain surfaces?
Yes. In terms of evidence, yes, I guess in terms of lab work, I mean, you can do this. As to a possibility, yes, there's absolutely a possibility. I think that this is one of the areas that we know very little about what happens when ions from the gas phase, and there's a whole, there's hundreds of ions, that in principle we could model now that would stick to the grains or to ice surfaces and potentially do something. We just don't know what they do, and it requires a lot of computational power to simulate those processes accurately, and a lot of, well, frankly, a lot of money and a lot of experts to do that, to the degree that we would need to put all of those processes into chemical models. And I think, I'm sure there are lab studies that could be done that would tell us a lot more about that as well. But currently we just have a really minimal knowledge of what happens. The expectation is that there is chemistry that happens, right? So when you have ions interacting with water, right, okay, you're going to have some kind of either chemical or physical interaction. But what happens then? What happens when you have an ion on a water surface with some other molecule present? Very often we find that, in the limited calculations that have been done, that the presence of the water itself changes the chemical properties of that system, of that ion molecule system. So there's a lot we don't know, and unfortunately, I can't really answer that question. And I just hope people do more work on this, and I'm not directly involved in it at present, but I think in the next 10 or 20 years, I mean, we're going to be forced to address this question. Yep.
Okay, thank you. So we are almost run out of time, but still short question. What kind of energetic processing of ices do you consider in your models?
So we currently have in these, so in the interstellar models, we currently have photoprocessing. That is to say, we sort of break this down into different pieces, but we photodissociate the ices, and then we separately consider subsequent reactions that can happen from those photo products. So we have photoprocessing that goes on. What some models have done is to introduce what's called radiolysis, which is where you have energetic particles of one kind or another, could be very energetic photons, but typically thought of as cosmic rays, that would ionize the ice, and as a result there would be various types of chemistry, either high energy chemistry going on, or just ions being produced in the ices. The models that I do for interstellar chemistry don't include that process. The reason for that is that I think actually it's a relatively small effect. I'm not saying that it doesn't have an influence, but I think it's outweighed quite strongly by the photo processing for various reasons that I don't have time to get into. In other regimes, for example, we have models that simulate ice chemistry in comets. Radiolysis is very important, and the reason for that is that cosmic rays that carry a lot of energy can penetrate very deeply into a comet, which is obviously a very thick body of ice and dust, whereas we don't have that same kind of problem or same kind of situation in the interstellar medium, where photons are able to penetrate the ices generally in the interstellar medium all of the time, whereas in a comet, your photons are going to penetrate to about 1 micron, but they won't go any further. Whereas cosmic rays or energetic particles can, in principle, go down to say 10 or more meters. But so it depends on the environment. Also, I think we generally don't have a great handle on how to include that in the chemical models. But yeah, some of us have begun that process, but I think there's a lot of work still to be done there.
Hey, thank you very much, Rob. Yeah, I think our time is already over for this lecture. So let's thank our lecturer for this very nice presentation. And yeah, with this, I would like to finish this lecture and still a good day. Yeah, goodbye.
All right. Thanks very much, everyone. Thanks, Sergey.
Bye-bye.